My topic for today is MLOps, why should I care? So the goal is to see what MLOps is and how it can actually help you on your current projects and what to do if you want to develop in this direction. So I believe all of you already know the terms, but just to set some ground rules, there are two definitions. Artificial intelligence, it's intelligence demonstrated by machines. It's also can be thought of like when machines try to make decisions, try to think. It's a general thing, right? And machine learning is a subset of AI. And machine learning basically is a set of algorithms that can improve based on the data. Once that's done, let's get to the topic. So there is a study conducted each year by CB Insights where they select 100 companies out of the companies that have AI as their main operational focus. And for us, it's not the study itself that's interesting, but the fact that that study had to select 100 companies out of 6,000 companies that have AI as a main focus. Just think about the number, like 6,000 companies, over 6,000 companies that specialize in some sort of AI. Of course, if we think about companies that just employ AI somewhere for some tasks, there are many more such companies than 6,000. So in the industry, we have lots of companies that want to do AI, that do AI already, and naturally that creates a lot of jobs. So according to the 2020 LinkedIn study, machine learning engineer is the fastest growing job in the US. Sorry. By the way, can you see the screen well? Something happened. Yeah, I assume it's yes. So what we need to understand here is whether machine learning engineers are enough to make AI projects happen. Let's take a look at the usual perception of an ML project. Let's say we have a data set and we have a problem statement. We understand that we need to do exploratory data analysis on the data set we have. We need to engineer some features. We have to try out different model architectures, select the best of them, and we need to deploy it. So nothing special, right? We estimate the model creation and around 5 weeks and the deployment process in 4 weeks. And by deployment process, we usually assume packaging the model in a Docker container and having a DevOps engineer deploy it, right? Nothing fancy. How it turns out in practice. So it doesn't go that smooth, actually. So first thing that we really understand is we want to get more data because our ML algorithms improve on the data. The more data, the better. We need to get more data. So that fixed training data set we were given at the very beginning is not enough anymore. To get more data and to ensure that the data is of high quality, because like in ML, garbage in, garbage out, we need high quality data, we have to build ETL pipelines for the data. That ETL pipeline is also like we even need a separate feature engineering pipeline for the model that's already deployed. Next thing is it turns out only like 1 or 2% on the team can really train our model. But we want the whole team to be able to do it. We want faster iterations. So we want the training to be reproducible. We want it to be automated. We also want to be able to collect training metrics just to compare the trains done by different team members, automatic trains, to see whether we are improving our metrics or not. We also need metrics for model serving, and in general, we want to be able to monitor the model. Because the models they get obsolete over time, and we want to be the first who find it out. Next thing is we want to be able to understand what the data set that we use to train the model. So for example, if we create a model for the healthcare, and this model like classifies whether there is an illness or not, and like in 2 months later the patient comes in and says, okay, why your model said that, we have to be able to debug it. So we need to store the data set for each model to be able to track the model back to the data set. And it appears to be a lot to ask from your machine learning engineers team. It even appears a lot to ask from a DevOps. For example, so we have a problem. We need to track the model back to the training data. How to do it? It's not really in a scope of a skill set of an ML engineer, and it's not something that DevOps should know how to do either. It's a different set of tools and a different a different way of building the processes. Also, let's say we have a deployed model. How to update it? By update, I mean to gather new data and to retrain it. So we need to be able to tell, first of all, when we want to update the model, and then we need to decide how we want to update our train test splits with the new data, how to retrain the model, and how to replace it, and so on. So during the production deployment, we start facing issues that neither ML engineers nor DevOps usually can answer. Yeah, so a bit of statistics, like around a quarter of projects are not deployed, they fail because the companies are not able to incorporate the ML processes in their practice. Let's take a look at a concrete example. So this is a template like I've seen several times in practice. For the sake of simplicity, let's say we are developing a model for the healthcare. We need to be able to classify X-ray images. Those images are packed in the DICOM files. You can think of them as a video stream of X-ray images. So we need just to unpack this file, extract frames from them, and classify each image separately. And we have developed a state-of-the-art PyTorch model for that. So looks like the biggest chunk of the work is done. We just need to deploy it, right? And we have several requirements for the deployment. So first of all, it has to be on GCP. The second thing is we prefer batch inference. Just a quick note, the difference between batch and online inference. Batch is when we have a job that looks at 1,000, 10,000 observations at a time and produce inference for each of them. And online inference is when we usually looking at one or a small number of observations and need to be able to produce the results in one request. So we get a request, we need to produce a response. The next requirement is we need to use GPU for inference to speed things up. So we need batch GPU inference on GCP. It's a pretty typical request. Like, what can possibly go wrong here? It turns out that a lot can go wrong with PyTorch on GCP. So on GCP, we have AI platform. That's exactly the tool for training and deploying models. But it does not support PyTorch as frictionless as it supports TensorFlow. So with PyTorch, the proper way to deploy it on a platform is to pack it in the custom containers. There are two other ways, but they are less than good. And with the custom containers, like the recommended approach, it turns out that they only support inline inference. And remember, we wanted the batch inference. Even if we could do the batch inference, it turns out that we cannot do GPU and batch inference. Okay, we say, let's do online inference with GPUs. So we spin a service that runs and waits for requests, right? And we will then scale the service down to 0 when we don't need that. And it also turns out that scaling to 0 is not supported out of the box for GPU services. So we are stuck in a corner. We have to do online inference with a GPU that are running 24/7. So we will be paying for that 24/7. And initially we wanted just batch inference to pay less. That's not a good solution, right? It sounds really expensive. So what can we do? There is a joke in computer science environment, like the theorem of software engineering. It says that any problem can be solved by introducing a new level of abstraction. And the modern theorem says any problem can be solved by introducing Kubernetes. So Kubernetes is ubiquitous everywhere, and why not to try it here? It turns out that Kubernetes plays really well here. So what are we proposing here? We deploy Kubeflow pipelines on top of Kubernetes, and that Kubeflow pipelines act as an orchestrator. We have two steps in our inference pipeline. The first step is to parse the frames out of DICOMs and assemble a batch data set out of them. And the second step is to perform the actual inference with GPU. In this setup, we are only paying for the GPU when we are doing this batch inference job, and we destroy the service afterwards. So looks like we've solved the problem, right? Let's implement that. The only problem with this setting is to implement it, we need 3 people with 3 different skill sets. Obviously, we need ML engineers, those who know the PyTorch, who know the Kubeflow pipelines, can work with BigQuery, like where the metadata of data set resides and so on. On the other hand, we need DevOps because we have introduced Kubernetes and it's a beast on its own. It has to be managed. It has to be troubleshoot. And the last role is data engineer. We have that data pipeline where we extract frames from DICOMs. We need to do it in a distributed fashion on a different technologies. So it turns out we need 3 different roles to deploy one model. That's really too many people for one model. What can we do? We can get MLOps engineer on the board. So what is MLOps? MLOps sits on the intersection of 4 different practices. First of all is data science. MLOps has to understand the ML workflow, how we train the models, like what are the artifacts. We have train, test, validation data sets. We have trained models itself. We need to understand the algorithms, the difference between supervised and supervised learning, and so on. So we need to know the data science stuff to understand what's going on. The next practice is data engineering. We need to be able to build ETL and feature engineering pipelines using big data technologies. This includes Spark, this includes Apache Beam, because in ML, the more data, the better. So we cannot just limit ourselves with pandas and do everything on one machine or just hope that Dask will help and do it on several machines. We have to be able to develop highly distributed jobs that can process terabyte of data and feed it in our model. The next practice is DevOps. As you saw, we usually work on Kubernetes. It's a huge system. We also have to be able to set up any piece of infrastructure that the ML project might need. For example, the labeling tool, or set up the deployed model, like to deploy the model in the containers, to scale it up. It's all DevOps skills. And the last but not least, it's software engineering, to glue all the things together. And besides, sometimes we need to develop APIs for the whole system, so the other services could use it. You can think of MLOps as a full stack developer in the machine learning world. As for the processes, here I have MLOps diagram as an extension of the DevOps diagram, where to the usual DevOps processes, we add the processes of data collection, model training, model validation, and it also adds some artifacts, most notably the data set and the trained model. So now, after we've shed some light on what MLOps is, let's see what practices it brings with it, because MLOps is a set of practices at the end. All of these practices but one, I'll mention which one, can be and should be applied to each and every project. So besides those practices are usually applied in the order I display them. So the first one that is foundational is reproducible model training. I think you can agree with me that in most projects, the only person who can really train the model is the one who developed it. It's set of Jupyter notebooks, set of scripts, the data set is hidden somewhere, like you have to perform the environment setup beforehand. So there are many things you have to consider to train a model. And the model training is the crucial part of every ML project. That's what makes this project alive, basically. So if we follow this practice, we need to make our model training reproducible and automatic. So the environment setup is taken care of, and the actual training workflow is also taken care of. And I just do not need to like run 6 notebooks in order to make that happen. The next practice is the data management. Of course, to train the model, I need the data. And the data is usually scattered over the infrastructure. So something resides on object storage, something is stored on mounted disks, whatever. So we need to gather data in one place where everyone can have access to it. And most importantly, we have to organize data in a form that everyone on a team can work with it. For this, we create two things, data lake and data warehouse. What's the difference? Data lake is for unstructured data and data warehouse is for structured data. Let me give you an example. So if we have an image data set, we will need both. The data lake will store the actual images, and the data warehouse will store structured data like the link to the image, the label, if we are talking about image classification, and other metadata about that image. So they are not mutually exclusive. On the contrary, they are usually used together. A different thing is a feature store. A feature store, so when you have the data in data warehouse plus data lake, you usually build some features on top of it, right? So you process the data in some way. And if those features are used by more than 2 or 3 people, it usually makes sense to put the processed feature somewhere so that each team member won't have to copy your feature engineering pipeline. That's a feature store. So you avoid code duplication and process duplication. Next thing, we are closing the loop by making the model training and deployment fully automatic. Remember, we already have the model training piece automated, and we already have the data stored in an accessible format. What we can do next is say that we want to retrain the model on each model code change, on each commit. And as a result of this process, we want to deploy the model for serving. This is called CI/CD CT. So CI/CD, I bet you know what's that, but CT is continuous training. The next practice, active versioning, is not needed in each and every project, but for some project, it's absolutely required. What this practice allows us to do is to track the trained model back to the actual data set it was trained on, and all the intermediate steps like engineered features, trained test splits, and so on. For example, consider a classic thing with credit scoring. Even if we did the prediction 3 months ago and the model is deprecated and we have a different model running in production, we have to be able to understand why that old model made the prediction 3 months ago, because it could be regulations, like we have to be able to respond to such inquiries, or it could be our internal analysis. And completing the picture, the last practice is model monitoring. When we deploy a model, we absolutely have to set up a monitoring mechanism. Otherwise, we are blind about our model, and when it gets obsolete, and it will definitely happen, our users will be the first to find out. And it's really hard to understand that the model is obsolete now, right? Because it's not a web service. It's not like it's working or not. It could be giving some predictions, and it's hard to say if they are wrong or not. So this practice said that we set up a monitoring pipeline, and the actual details of it can be different. For example, we say that we have a new data coming in and you label data, right? Because it's hard to do something with the data that has not yet been labeled. But when we get new label data coming in, we score our model on that new data and see if our key performance metrics are above the thresholds. If they are not, the model is obsolete, and we can automatically trigger retraining because we already have an extended data set. We already have the new data in our data set, right? So those are the best practices. And let's also take a look at MLOps tools that we use. These are the tools that are not dependent on a particular cloud. So you may use them on the cloud, you may use them on premise. So first and foremost is Kubernetes. Basically, almost all of the services you're using nowadays are based on the Kubernetes, and ML is not an exception. So it's an orchestration tool for containers, to put it simple. The next thing is Kubeflow. It's a one-stop shop for machine learning on Kubernetes. It offers Jupyter notebooks. It offers machine learning workflow orchestration. It offers automatic hyperparameter tuning. It offers model serving. And it's an open source project started by Google and supported by Google. And it got a lot of traction since then. So the next thing is smaller. MLflow, it's a creation of Databricks, and it consists of 3 sub-projects. The first one is tracking. It allows you to track metrics while you are experimenting with the model. Sorry. And the next thing is models. It allows you to deploy models, and it also has a model registry. And the last thing is projects, where you can share your environment within your team easily. But what MLflow does not offer is the data versioning. So it can only version your models, but not your data. And here DVC comes in. DVC allows you to version your data as like you are versioning your code with Git. There is another interesting development called Pachyderm. It's basically 3 things in one package. The first thing is an orchestration tool, so you can create reproducible training using it. The second thing is the big data processing tool. It's a map reduce tool. You can divide your several terabytes of data set between different workers and process it. And the last thing, it's really strong data versioning. So Pachyderm, again, like Git, has commits, but it stores models and data in those commits and allows you to track those back to original data sets. And just out of curiosity, let's see what we have on GCP. AI platform is a system for model training and model deployment. BigQuery is a data warehouse. It stores structured data, and it also allows you to run SQL queries on terabytes of such data. Dataflow is for feature engineering pipelines, for data processing pipelines, both batch and streaming. Composer is an orchestration tool, and PubSub is a messaging system used to glue it together. There is an interesting project called TensorFlow Extended. It basically allows you to do MLOps inside the TensorFlow ecosystem. So including data processing, like your feature engineering pipelines, and model deployment and model monitoring, it's all inside. Yeah, just to give you a small taste of what MLOps engineer usually does. So it's a real architecture we've done for one of our internal projects. And the task was, so we have a stream of Bitcoin transactions, and we need to do an anomaly detection in the transactions. The interesting part was that that system has a UI where a client can control the sensitivity, so the threshold for this anomaly detection. And as you could have guessed by now, each different sensitivity threshold means a new model. So each time a client changes the threshold in UI, we had to be able to create a new model and deploy it on the fly. And it is also complicated by the fact that Bitcoin transaction data is actually a streaming data, so it's unbounded data set that's always coming in. How it was solved? So each time we detected a new sensitivity threshold, we had an orchestrator, a composer, number 9 on the diagram, that started an AI training job, a platform training job, sorry. So after this training job, we got a model that we added to our streaming pipeline using a combination of a data flow pipelines plus PubSub. The idea of this diagram is to show that the goal of an MLOps engineer is to envision the whole architecture of an ML project. So that data scientists know like what will be the place for the model and how the model will be used, and DevOps engineer know what will be the infrastructure and how to deploy it. And it also shows that we get really interesting stuff sometimes, and the complexity is fascinating. Yeah. So that was my presentation. A couple important points after it. So we are currently looking for MLOps engineers. And even if you're not MLOps engineer, but you'd like to become one, it's not a problem. We are starting a retrain program for data scientists, software engineers, and DevOps engineers. So those are the backgrounds we consider, and we cover all the rest to grow a full-fledged MLOps engineer. So thank you for the attention. Let's get back to questions.